Hello friends, welcome to my YouTube channel Tech Guru Gautam Prasad, and let me welcome you once again to the Fundamentals of Electrical Classes Part 2. So in this Part 2 we are going to further explore into the AC fundamentals. We will delve deep into the areas of basics of AC fundamentals. So, as I told you in the earlier class, this RMS means root mean square value, and it has this is the positive half cycle that has been shown in the picture, which on the x-axis time is there, and on the y-axis you have voltage. So on the sine wave, you can see you have V1, V2, V3, V4, V5, V6, V7, and up to V12. These voltages are voltages at different time intervals, and the values of amplitude has been taken. Okay, now having got these values, you will have to square them, and you will have to uh, sum the squares and divide it by the number of the readings that you have taken, and then you have to find out the square of the whole thing, the square root of the whole thing. So that is called root mean squared. In short, that is called root mean squared value. RMS voltage is sometimes also said to be it is DC equivalent of AC, and that has been shown in this picture here. So on the left side of the picture you have been shown a full cycle of AC wave, and on the right side you have been shown a DC voltage of 240 volt. So here RMS value is of the AC wave is 240 volt, and that sometimes can be said to be 240 volt of DC available. Basically what happens, DC gives you the clear picture of the power generated in the circuit in terms of voltage into current. Okay, and in the case of AC, it is not simply voltage into current, but also there is something called power factor, and power factor could be any figure between 0 to 1. So the typical value is 0.8 for all practical applications, but this power factor reduces the value of the power, because mm, having taken 0.8, if V into I is 100 and power factor is 0.8, it becomes 80 volt in place of 100 volt. So that is how we look at this. So sometimes RMS value is a value that is lesser than the peak value. So it stands below, as you have been shown by the dotted line here in the picture, and this dotted line of the sine wave shows you the RMS value of the voltage. So RMS value is also known as DC equivalent of the AC. So now here the values uh, at different angles, basically time is also read as angle. So at 18 degree, 36 degree, 54 degree, 72 degree, 90 degree, 108 degree, 126 degree, 144 degree, 162 and 180 degree. These values have been taken, and the voltage values have been given here, and they have been squared and summed up and divided by 10, because 10 number of divisions have been taken. And after summing up and summing up the square values and dividing it by 10, we are taking the square root of the whole thing, and that sometimes becomes a value of 14.14 volts. Okay, so the peak value, please bear in mind that this peak value at 90 degree is 20 volt. Okay, that is it. I'm scrolling because I'm touching upon the the important things only. VRMS is equal to, thus becomes VPK, that means peak value multiplied by 0.707, or you can say V peak by root 2. 1 by root 2 has got the value of 0.7071. So if you take the peak value 20 volt multiplied by 0.7071, it comes up to be 14.14 volts. So that this is the RMS value for the 20 volt AC wave, sine wave. Okay, that is it. RMS voltage. Now let us talk more about this average voltage. So average voltage in the similar fashion as you squared and summed up everything. Here you don't have to square. In fact, you have to take all those values and sum directly without squaring. So you sum the voltages V1, V2, V3 up to V12 and then divide it by number of divisions, number of samples taken. So samples, number of samples is 12. So here V1 to V12 sum has been divided by 12. So average value is this value. Taking a better scenario, here this again, as we had taken in the case of RMS value, here also we have taken the values for several angles, 18 degree, 36 degree up to 180 degree, and we have summed up the total values and divided by 10. Now this comes to be 12.64. In the earlier case, in the case of RMS value, it was 14.04, perhaps. It was, what was the exact value? Let me tell you. Uh, it was, I will scroll and reach to, it was 14.14 volts. Okay. So now you are getting a lesser value in the case of average voltage. So here it is not 14.14, but it is 12.64 volt. So you have to remember here the average voltage is lesser than the RMS voltage. So average voltage cannot be taken to give the true picture of the power consumption in the AC circuit. That is why we are not taking average value, because it is not giving us the true picture of the power consumption in AC circuit. That is it. So here you look at this picture, this 63.7% is the value of the average voltage. This line has been drawn to show you that this is the level of the average voltage, and positive average value is this. And then you have negative average value for the negative half cycle. Obviously, for the negative half cycle, if you sum up the different divisions as we have done for the positive half cycle, you will get a negative value. So we have a negative peak, a positive peak, and negative average value, and a positive average value. All right. So these are all for the analysis purpose, how this AC wave is behaving. Now, looking at these two, average value and RMS value. In this picture, you can say, you can see this RMS value is 70.7% and average value is 63.7%. Okay, so these two levels have been shown. So compared to peak value, the 70.7% stands below that, and 63.7 stands below this RMS value. So these are the levels of average value and uh, uh, RMS value and the peak value. So you can take a comparative look of all these three values together in this graph. Now, this is a triangle that is called power triangle in the case of AC circuit. So here it gives, I was talking about the power factor. So here you can see uh, this diagonal of this rectangular triangle, right angle triangle is uh, apparent power. Apparent power. That means in the circuit it appears to consume this much of power, but actual power is something different, and that is shown by active power. Active power is the real amount of the power that is being consumed in the circuit, not uh, unreal one. And there is something called reactive power that is represented by Q. Active power is, of course, represented by P, and apparent power is represented by S. So, uh, active power is V into I into cos phi, V being voltage, I current, and cos phi is the power factor. Reactive power Q is V into I into sine theta, and apparent power is simply the multiplication of voltage and the current. So if you look at this, you will observe that you have got a relationship between P and Q. You know, active power is equal to apparent power multiplied by power factor. So power factor becomes how much? Active power in watt. Active power is always measured in watts, and apparent power is measured in volt amps. So if you divide active power by apparent power, you will get the power factor of the circuit, of a particular circuit. Okay. So there is a relationship between P, Q, and S I was talking about. You can see S is equal to S being the hypotenuse of this right angle triangle. So this hypotenuse is equal to square root of P square plus Q square. This is a very popular relationship. You must be able to understand why it is so. Okay. So according to trigonometry, you can understand this hypotenuse is the square root of perpendicular square plus base square, or base square plus perpendicular square. So how can we better understand this uh, the relationship of active power, reactive power, and apparent power? So it has been represented here with a glass of beer, so which is partially empty. If you look at the top part of the glass, this is empty. This is covered with uh, foam. So this part is not having any beer as such, but it appears to be full. Okay, so this is the apparent power. This full glass is representing the apparent power. The amount of the beer it actually has, the glass has, is the active or the real power, and the amount of the glass which is covered with foam is called the reactive power. So, active power is the real power that is being consumed in the circuit, and reactive power is consumed, but you don't, you know, get the advantage, any advantage of this power. So, where it is consumed, that is a matter of discussion at a later stage to understand this properly. So, let's proceed here. Now, you must have heard about the harmonics. So, harmonics are basically unwanted higher frequencies which are superimposed on the fundamental waveform, creating a distorted wave pattern. So, these harmonics tend to distort your real sine wave. So, harmonics are unwanted kind of thing, uh, in the real sine wave, and they should not be there. But somehow, because of the circuit elements, certain type of circuit elements, they come into the picture into the circuit, and they disturb the fundamental wave of the voltage or current, and they need to be eliminated or suppressed in the circuit, because any deviation from the fundamental wave is a kind of loss for you. So what is the fundamental frequency for RAC wave? It is 50 hertz. So apart from the 50 hertz frequency, if you are getting some other frequency superimposed on the uh, voltage or the current wave, the fundamental wave, then it is frequency. Normally, we have seen the harmonic frequencies are multiple of the fundamental frequencies, like it, it will be double of the fundamental frequency of 50 hertz, that means 100 hertz, 150 hertz, 250 hertz, 200 hertz. Okay, so uh, second harmonics consists of 100 hertz, 2 into 50. Third harmonics, 3 into 50, that means 150 hertz. Fifth harmonics, 100, 250 hertz. Seventh harmonics, 350 hertz, and so forth. Likewise, given a 60 hertz fundamental waveform, the second harmonics, the third harmonics, fourth harmonics will be like 120 hertz, 180 hertz, 240 hertz, and 300 hertz in the case of 60 hertz fundamental frequency wave. Okay, 60 hertz of the frequency is used in USA, and 50 hertz is used in our India. So now you can see here the complex waveform due to the harmonics. You know, here this is the first fundamental harmonics. This one is the fundamental harmonics. This is the output complex uh, waveform due to harmonics. What happens actually? So here, if you look at this second picture, it has got the frequency of second harmonics, and third harmonics has got a thrice frequency than the fundamental frequency. And similarly, if you look at the fourth harmonics or the fifth harmonics, they have higher frequency. So if they mix up, now how will be the resultant wave? So you can see this is the first wave, fundamental one with purple color, and then you have another frequency which is fundamental frequency in purple wave, and then you have in green color you have the second harmonics, and they together make this red color wave. When they mix up, they are not exact sine wave that we expect to be. If third harmonics is superimposed on the fundamental wave, this creates this type of red color. Here it has been shown. So the resultant is distorted one. So you will not get the pure sine wave. So what happens if you don't get the pure sine wave as the output or in the circuit? Okay. So there are losses associated with the harmonic frequencies, and that is why harmonic losses are unwanted losses. Okay. So excessive heating happens as a result. Motor torque problem in the case of reverse direction, it is saying in the forward direction excessive heating. Okay, that is the type of the problem you will face. So that's all for this discussion. I hope this must have added value to your knowledge, and you will appreciate the discussion. Thank you very much for being with me uh, on this video. Thank you so much.